Picture this: you take a single step through a swirling vortex of light, and in an instant, the stars blur past you. The fabric of space-time twists like a cosmic ribbon, and suddenly, you're standing on the other side of the galaxy. A place that should have taken lifetimes to reach is now just a heartbeat away. This isn't just a scene ripped from the pages of a sci-fi novel. It's the tantalizing promise of wormholes, hypothetical tunnels through the very fabric of reality. Could these mysterious portals actually exist, bridging unimaginable distances in the blink of an eye? Or are they forever confined to the realm of science fiction, teasing us with possibilities just out of reach? The idea of wormholes has captivated scientists and storytellers for decades, straddling the line between cutting-edge physics and the wildest corners of human imagination. In theory, these cosmic shortcuts could bend space-time itself, creating a bridge between two distant points in the universe. Imagine folding a piece of paper so that two dots touch. That's the basic principle. But the reality is far more complex, tangled up with mind-bending concepts like dark matter, black holes, and the very nature of existence. Even Einstein's equations hinted at their possibility, yet the question remains, could we ever harness such a phenomenon, or would it always remain a breathtaking idea just beyond our grasp? From blockbuster movies to the frontiers of theoretical physics, wormholes embody humanity's deepest yearning to explore the impossible. They represent the ultimate adventure, a doorway to the unknown that challenges everything we think we know about the universe. And that's exactly what we're diving into today. We'll unravel the science behind these enigmatic portals, separate fact from fiction, and explore what it would truly take to step through one. Whether you're a science enthusiast, a dreamer, or just curious about the cosmos, this journey will take you to the edge of what's possible and maybe even beyond. Strap in, because we're about to bend the rules of reality. To understand how wormholes could exist, we need to rewind back to one of the most revolutionary ideas in physics, Einstein's theory of general relativity. In the early 20th century, Einstein turned our understanding of gravity upside down. Instead of a simple pulling force, he proposed that massive objects like stars and planets actually warp the fabric of space and time around them. Picture setting a bowling ball on a trampoline. The surface bends under its weight, creating a dip. Now, if you roll a marble nearby, it spirals toward the bowling ball, not because of some invisible string tugging it, but because the surface itself is curved. That's essentially how gravity works in Einstein's universe, not as a force, but as the bending of space-time itself. Now, here's where things get wild. If space-time can bend, could it fold? Could two distant points, stretched far apart in the normal fabric of the cosmos, suddenly touch if space is twisted in just the right way? That's the tantalizing possibility buried in Einstein's equations. In the late 1930s, physicists Albert Einstein and Nathan Rosen explored a peculiar solution to these equations: bridges connecting separate regions of space-time. These hypothetical structures, later dubbed Einstein-Rosen bridges, became the foundation of modern wormhole theories. But how would a wormhole actually function? Imagine space-time as a vast sheet of paper with two dots drawn on opposite ends. For a spaceship traveling normally, the journey between them would be a straight line, an immense distance. But if you fold the paper so the dots overlap, suddenly there's a shortcut. A wormhole would be like piercing a pencil through that folded point, creating a tunnel connecting both sides. The math suggests that under extreme conditions like the titanic gravitational forces near a black hole, such tunnels might form naturally, warping space-time so severely that two distant locations briefly stitch together. Of course, the universe rarely makes things simple. While the math allows for wormholes, the practical challenges are staggering. For one, these cosmic shortcuts would likely be incredibly unstable, snapping shut the instant anything tries to pass through. Some theories suggest that only an exotic form of matter, something with negative energy could prop them open long enough to traverse, and that's assuming they don't instantly collapse into a black hole or unleash forces that would shred anything daring to enter. Yet, despite these hurdles, the fact that wormholes emerge at all from the equations of relativity is astonishing. They remind us that the universe, in all its strangeness, might still hold surprises we've barely begun to imagine. Not all wormholes are created equal. In fact, physicists have theorized several distinct types, each with wildly different properties, some offering the potential for interstellar travel, others serving as cosmic dead ends. Let's start with the most basic divide: traversable versus non-traversable wormholes. Non-traversable wormholes, like the original Einstein-Rosen bridges, are more like mirages in the fabric of space-time. They might form momentarily under extreme gravitational forces, such as when black holes collide, but they'd collapse instantly, crushing anything that dared to enter. These are the universe's one-way doors. You could theoretically fall in, but you'd never make it to the other side. Traversable wormholes, on the other hand, are the holy grail. These hypothetical structures would remain stable long enough for matter, or even a spacecraft, to pass through unharmed. But here's the catch: keeping a wormhole open requires something bizarre called exotic matter. Unlike ordinary matter, which gravitationally attracts, exotic matter would need to exert negative energy or repulsive gravity, effectively propping the wormhole's throat open like cosmic scaffolding. The problem: we've never observed such matter in nature. Some theories suggest quantum fluctuations or advanced civilizations could manipulate it, but for now, it remains a speculative lifeline for interstellar shortcuts. Now let's dive deeper into geometry. Lorentzian wormholes, named after the physicist Hendrik Lorentz, are the classic time tunnel models we see in pop culture. They exist within our familiar four-dimensional space-time, where time flows forward and the laws of relativity hold firm. These are the wormholes that could, in theory, connect distant star systems or even different eras, though the time travel implications get messy fast. Imagine stepping into a Lorentzian wormhole on Earth and emerging near a planet orbiting Alpha Centauri, but due to time dilation, centuries might have passed back home. Euclidean wormholes, by contrast, belong to the realm of quantum mechanics and imaginary time. These are less like tunnels and more like ephemeral quantum foam, tiny, flickering structures that might exist at the Planck scale, the smallest possible measurement in physics. They're not for traversing galaxies, but could play a role in theories of quantum gravity or even the birth of universes. Picture space-time at this scale as a bubbling sea, with wormholes constantly forming and vanishing in a chaotic dance. Then there's the Schwarzschild wormhole, a specific solution tied to the physics of black holes. Named after the physicist Carl Schwarzschild, this model describes a non-traversable bridge linking a black hole to a theoretical white hole, a region of space where matter and energy explosively pour out instead of collapsing in. While white holes remain purely hypothetical, the idea tantalizingly suggests a way black holes might vent into another universe. But don't pack your bags yet. Crossing a Schwarzschild wormhole would require surviving the black hole's crushing singularity first, something no known material could endure. What does all this mean for the dream of space travel? Traversable Lorentzian wormholes offer the most promise, but their stability hinges on exotic physics we've yet to master. Non-traversable and Euclidean wormholes, while fascinating, serve more as cosmic thought experiments than practical shortcuts. Yet even the most theoretical models push our understanding of space-time to its limits, hinting at a universe far stranger than we've dared to imagine. Whether any of these wormholes exist or could ever be harnessed remains one of physics' greatest open questions, but the mere possibility keeps scientists dreaming and explorers gazing at the stars with renewed wonder. The Einstein-Rosen bridge wasn't born from a quest for interstellar travel. It emerged almost by accident, a curious byproduct of scientists wrestling with the bizarre implications of Einstein's relativity. In 1935, Albert Einstein and his collaborator Nathan Rosen stumbled upon something unexpected while trying to solve equations describing black holes. Their calculations revealed a strange mathematical loophole, a hidden connection between two separate regions of space-time, like a hidden tunnel stitched into the universe's fabric. At the time, they weren't imagining cosmic shortcuts or portals to distant stars. They were simply trying to refine our understanding of gravity's most extreme environments. What made this theoretical bridge so unusual was its structure. Unlike the wormholes of science fiction, the original Einstein-Rosen model didn't offer a survivable passage. Instead, it acted more like a cosmic trapdoor, a fleeting connection between a black hole and its hypothetical mirror image, a white hole. Picture a funnel with two narrow necks pointing away from each other, linked by an impossibly thin throat. Anything crossing this bridge would encounter what physicists call a singularity, a point of infinite density and gravity where the laws of physics break down. In other words, the bridge existed mathematically, but in practice it would collapse faster than anything could traverse it, crushing matter into oblivion. Einstein and Rosen initially saw their discovery as a way to eliminate singularities from the equations, smoothing out the mathematical roughness of black holes. They hoped these bridges might prove that singularities were just artifacts of incomplete theories, not real physical phenomena. Ironically, their work inadvertently revealed that singularities might be unavoidable, and that space-time could twist itself into even stranger shapes than anyone had predicted. The Einstein-Rosen bridge became less a roadmap for travel and more a glimpse into the universe's capacity for cosmic weirdness. For decades, physicists dismissed these bridges as mathematical oddities interesting in theory but irrelevant to the real universe. That changed in the 1950s when physicist John Wheeler took a fresh look at the concept. He was the one who coined the term wormhole, envisioning these structures as tunnels burrowing through space-time like an apple worm chews through fruit. Wheeler's playful analogy shifted the conversation, transforming Einstein and Rosen's abstract equations into a canvas for speculation. Could stable wormholes exist? Could they connect not just two points in space but different times, or even alternate universes? The original Einstein-Rosen bridge remains a cornerstone of wormhole physics, not because it's practical, but because it proved space-time could bend in ways that defy intuition. It showed that the universe's rulebook might contain pages we haven't even glimpsed yet, pages where distances collapse, tunnels form, and the unimaginable becomes mathematically possible. While later theories would explore traversable wormholes and exotic matter, Einstein and Rosen's accidental discovery reminds us that sometimes the most revolutionary ideas emerge not from chasing dreams, but from daring to follow the math wherever it leads. Black holes and wormholes might seem like cosmic cousins, both bending space-time to their will, but their relationship is far more complex and mysterious than it appears. At first glance, a black hole seems like the ultimate dead end, a point of no return where even light gets swallowed forever. Yet some theories suggest that hidden deep within a black hole's crushing embrace, there could be a gateway, a wormhole waiting to whisk matter away to some distant corner of the universe, or even to another universe entirely. It's a dizzying possibility, one that blurs the line between destruction and transportation, between cosmic oblivion and interstellar shortcut. To understand how this might work, let's peer into the heart of a black hole. As you approach one, space-time warps so severely that time slows to a crawl, and gravity stretches everything into spaghetti like strands, a process ominously called spaghettification. But what lies at the very center, according to general relativity, a singularity awaits, a point where density becomes infinite, and the laws of physics as we know them cease to function. Here's where things get speculative. Some physicists propose that instead of a singularity, there might be a Planck star, a highly dense but finite object, or even a tunnel through space-time itself. This tunnel, the hypothetical wormhole, wouldn't behave like the pristine portals of science fiction. Crossing it would be like surfing a tsunami through a collapsing cave. The intense gravitational forces would stretch and compress anything entering in a chaotic dance, and the wormhole itself might snap shut in an instant. But if exotic matter or some yet unknown force could stabilize it, the black hole's interior might not be a grave after all, but a backdoor to somewhere else entirely. The idea gains traction when you consider rotating black holes, known as Kerr black holes. Unlike their static counterparts, these cosmic whirlpools don't just crush matter, they twist space-time around them like a vortex. Some solutions to Einstein's equations suggest that a Kerr black hole singularity might form a ring rather than a point, creating a theoretical passageway. If you could navigate the violent forces around it, you might emerge in another region of space-time. Of course, the challenges are staggering. For one, no material known could survive the trip. Even if a wormhole exists inside, the radiation and tidal forces near the black hole's event horizon would vaporize anything long before it reached the center. And then there's the issue of time. Due to extreme gravitational time dilation, crossing a black hole's threshold might mean centuries pass in the outside universe by the time you emerge elsewhere, if you emerge at all. Yet the mere possibility keeps scientists theorizing. Could advanced civilizations harness black holes as natural wormhole generators? Could quantum physics reveal stabilizing mechanisms we haven't yet imagined? These questions push the boundaries of both astrophysics and philosophy, forcing us to confront how much we still don't understand about the universe's most extreme environments. Black holes might not be the end. They could be the beginning of a journey we're only starting to map. The biggest obstacle standing between us and real, traversable wormholes isn't just the mind-bending physics, it's something far stranger. To keep a wormhole stable enough for anything to pass through, you'd need a substance that defies everything we know about the universe, exotic matter. Unlike ordinary matter that makes up planets, stars, and even black holes, exotic matter would have to possess something called negative energy density. That means instead of being pulled together by gravity, it would repel, pushing outward with a force that could counteract the natural tendency of a wormhole to collapse in on itself. Think of it like trying to hold open the jaws of a giant cosmic vice. Exotic matter would be the unbreakable wedge keeping them apart. But here's the catch: no one's ever found this mythical material. Everything we've observed in nature, from the air we breathe to the dark matter hiding in galaxies, responds to gravity the same way. It attracts. Exotic matter would have to flip this script entirely. The closest we've come to glimpsing something similar is in the bizarre realm of quantum mechanics, where tiny particles can briefly borrow energy from the vacuum of space itself, creating what's known as negative pressure. These fleeting quantum fluctuations hint that the universe might allow such behavior on a microscopic scale, but scaling that up to something big enough to hold open a wormhole. That's like trying to build a suspension bridge out of soap bubbles. Even if exotic matter exists, the numbers don't inspire optimism. Theoretical models suggest you'd need staggering amounts of it concentrated in precise configurations to stabilize even a modest wormhole. Some calculations estimate the energy equivalent of converting entire stars into this mysterious substance just to keep a single portal open for a fraction of a second. And then there's the question of control. Negative energy density doesn't just defy gravity. It could unravel causality, creating scenarios where effects precede causes. That's not just an engineering challenge, it's a paradox waiting to happen. Yet the hunt for exotic matter isn't purely science fiction. Experiments with something called the Casimir effect have shown that empty space isn't truly empty. it seethes with virtual particles popping in and out of existence. Under the right conditions, this quantum foam can produce measurable negative energy between closely spaced metal plates. It's a far cry from stabilizing a wormhole, but it's proof that the universe might permit such anomalies in controlled settings. The leap from lab-scale curiosities to cosmic-scale engineering, however, remains unimaginably vast. Perhaps the most tantalizing idea is that exotic matter isn't something we'd find, it's something we'd create. Advanced civilizations harnessing technologies we can't yet fathom might synthesize it through manipulation of quantum fields or higher dimensional physics. But for now, exotic matter remains a phantom in the equations, a placeholder for a solution we haven't discovered. Without it, wormholes stay firmly in the realm of theory, beautiful, beguiling, but always just out of reach. The dream of stepping through a cosmic shortcut isn't impossible, but it's locked behind a door we don't yet have the key to open, and that's what makes the search so thrilling. Every new breakthrough in quantum physics, every deeper probe into the fabric of reality, inches us closer to answering whether the universe might allow such magic after all. What if stepping through a wormhole didn't just take you across space, but across time itself? This isn't just a sci-fi trope, it's a tantalizing possibility buried in Einstein's equations. The key lies in motion. Imagine one end of a wormhole anchored near Earth, while the other gets strapped to a spaceship and accelerated to near light speed. Time dilation kicks in, a quirk of relativity where high speeds slow time for the moving object relative to the stationary one. After a year on the ship, decades might pass on Earth. Now here's the twist: step through the moving end, and you'd emerge in Earth's past relative to your own timeline. Return through the wormhole, and you'd arrive back before you even left. A closed time loop crafted by the universe's own rules. But time travel through wormholes isn't as clean as flipping a calendar. The grandfather paradox looms large. What if you traveled back and accidentally prevented your own birth? Physics has a few answers, some stranger than fiction. One solution is the self-consistency principle, where the universe corrects any contradictions like a cosmic editor. Your actions in the past would already be part of history, woven seamlessly into events so they inevitably lead to your existence. Try to erase your grandfather, and some quirk of fate, a missed bullet, a sudden change of heart would always intervene. The universe, in this view, tolerates time travel but forbids paradoxes. Then there's the multiverse workaround. Every trip through a wormhole might spawn a branching timeline, separating your altered past from the original. In this scenario, you could indeed alter history, just not your own. The timeline you leave behind remains untouched while you carve a new path in a parallel universe. It's less like rewriting a book and more like starting a sequel with a different plot. Wormholes, in this context, wouldn't just bridge moments in time, they'd bridge entire realities. Yet the challenges are as dizzying as the possibilities. Stabilizing a wormhole long enough to enable time travel would require unfathomable energy, precise control over exotic matter, and a way to survive the gravitational turbulence at its throat. Even if you succeeded, the tiniest miscalculation could strand you in an era with no way back, or worse, unravel causality entirely. The laws of physics might permit time loops mathematically, but they seem to guard them with near impossible hurdles. Perhaps that's for the best. Time travel isn't just a technical problem, it's a philosophical minefield. Could we trust ourselves with the power to rewrite history? Would the fabric of reality fray under repeated meddling? Wormholes offer a window into these questions, blending hard science with existential wonder. They remind us that the universe's deepest mysteries aren't just about how things work, but whether we should ever dare to twist them. Quantum mechanics and wormholes might seem like strange bedfellows. One governs the impossibly small, the other the unimaginably vast, but beneath the surface, they could be two sides of the same cosmic coin. One of the most startling revelations in modern physics is the idea that quantum entanglement, that eerie connection where particles instantly influence each other across vast distances, might actually be a kind of microscopic wormhole in disguise. This mind-bending connection goes by a deceptively simple name, the ER equals EPR conjecture. It proposes that the Einstein-Rosen bridges we associate with wormholes are fundamentally linked to the phenomenon Einstein famously derided as spooky action at a distance. The conjecture stitches together two of Einstein's own discoveries that he never connected in his lifetime. The refers to the Einstein-Rosen bridge, the original mathematical wormhole. The EPR stands for Einstein, Podolsky, and Rosen, the trio who first highlighted the paradox of quantum entanglement. At first glance, these ideas couldn't seem more different. Entanglement involves particles like electrons or photons mirroring each other's states instantly, no matter how far apart they are. Wormholes, on the other hand, are cosmic shortcuts through warped space-time. But in the equations of quantum gravity, they might be describing the same underlying reality, just from different angles. Picture two entangled particles as the mouths of a wormhole so tiny it exists only at the Planck scale, far smaller than an atom. Though they're separated by light years in ordinary space, they're literally connected through a higher dimensional bridge. This would explain entanglement's instantaneous link without violating relativity's cosmic speed limit. The particles aren't communicating faster than light, they're just taking a hidden shortcut. It's like two people whispering through a secret tunnel while everyone else assumes they're shouting across a valley. The implications ripple across physics. If ER equals EPR holds true, it could revolutionize our understanding of black holes. Quantum information falling into a black hole might not vanish forever. It could be transmitted through a wormhole network to another point in space-time, preserving the universe's fundamental rules against information loss. This idea gained traction in recent years through holographic principal theories, which suggest our three-dimensional reality might be a projection of information stored on a two-dimensional surface, with wormholes acting as the hidden circuitry connecting it all. Yet the conjecture remains speculative, a tantalizing hypothesis without direct proof. Some physicists argue it's more of a suggestive metaphor than a literal description, while others believe it could unlock quantum gravity's deepest secrets. Experiments to test these ideas are fiendishly difficult, probing Planck-scale structures or creating controlled entangled systems massive enough to exhibit space-time effects pushes current technology to its limits. But the mere possibility reshapes how we view the fabric of reality, blurring the line between the quantum world and the cosmos at large. Perhaps most intriguing is what ER equals EPR implies about the nature of space itself. If entanglement and wormholes are fundamentally linked, then space-time might not be the smooth, continuous stage we perceive. It could be a vast, dynamic network of quantum connections, stitched together by countless microscopic bridges. The empty void between stars would teem with hidden structure, and the universe's grandest phenomena could trace back to the smallest threads of quantum mechanics. It's a vision of reality where the very concept of distance becomes fluid, and the universe's most intimate connections might be hiding in plain sight. Cosmic strings sound like something straight out of mythology, ancient threads woven through the fabric of reality itself. These hypothetical one-dimensional cracks in space-time, thinner than an atom but stretching across the entire universe, carry mind-boggling density. A single centimeter of cosmic string could weigh as much as a mountain, warping space-time around it like a steel wire resting on a stretched rubber sheet. And here's where things get wild. Some physicists speculate these cosmic filaments might be the universe's ultimate scaffolding, capable of propping open, stable wormholes. The idea hinges on the immense gravitational influence of cosmic strings. According to general relativity, any object with mass bends space-time, but cosmic strings do it in a peculiar way. Unlike planets or stars, which create spherical dips, a cosmic string would warp space-time into a sharp, cone-like shape. Now, imagine two such strings moving parallel to each other at near light speed. The space-time between them would twist so dramatically that it could theoretically pinch into a tunnel, a wormhole. It's like pulling two threads taut on a piece of fabric until the material between them buckles and forms a hole. But why would cosmic strings offer an advantage over exotic matter? The answer lies in stability. While exotic matter remains purely theoretical, cosmic strings, if they exist, are predicted by well-established models of the early universe. In the fiery chaos following the Big Bang, rapid phase transitions in the newborn cosmos might have left behind these defects like cracks forming in ice as it freezes. If even a few survived to the present day, they'd be gravitational powerhouses, potentially capable of warping space-time without the need for hypothetical negative energy. The logistics, however, are daunting. To create a traversable wormhole, you'd need to maneuver cosmic strings with precision approaching the impossible. Picture trying to thread two needles moving at a fraction of light speed while they're separated by light years. Even a slight miscalculation could snap the strings or send them spiraling away, collapsing the wormhole in an instant. And then there's the energy problem. Accelerating objects with the mass of entire mountain ranges to near light speed would require energy sources far beyond anything we can conceive. Yet the tantalizing possibility remains. Some theories suggest advanced civilizations, if they exist, might harness cosmic strings as natural wormhole generators, weaving interstellar gateways from the universe's own primordial scars. Others propose that certain types of cosmic strings could naturally form closed loops, creating self-stabilizing wormholes without any outside intervention. It's a reminder that the universe might have already built the tools for interstellar travel. We just haven't learned to recognize them yet. Of course, cosmic strings themselves remain elusive. Despite decades of searching, no direct evidence has been found, though astronomers have hunted for their subtle signatures, distortions in the cosmic microwave background, or strange gravitational lensing effects around seemingly empty patches of sky. Their existence would validate key predictions of string theory and quantum field theory, while their absence would force physicists back to the drawing board. Whether cosmic strings are the key to practical wormholes or merely another fascinating dead end, their study pushes the boundaries of what we consider possible. They embody the spirit of theoretical physics, dreaming big, following the math, and daring to imagine a universe far stranger than fiction. And if they do exist, weaving their way unseen through the cosmos, they might just hold the blueprint for humanity's greatest adventure. Wormholes have long been the playground of storytellers, bending not just space-time but the limits of imagination in films, books, and TV shows. Take Interstellar, where a gargantuan wormhole near Saturn becomes humanity's lifeline to a new home. The film's portrayal leans heavily on real physics, consulting Nobel laureate Kip Thorne to ensure the wormhole's lensing effect and spherical shape mirrored scientific predictions. Yet it takes creative liberties like the interior's kaleidoscopic tesseract, blending hard science with poetic speculation. Compare that to Stargate, where wormholes are sleek, shimmering portals activated by ancient alien technology. Here, the science takes a backseat to adventure. Travel is instantaneous, with no time dilation or gravitational chaos, making it more fantasy than physics. Then there's Doctor Who, where the TARDIS treats wormholes like cosmic back alleys, weaving through time and space with whimsical disregard for Einstein's equations. The show's wormholes are less about accuracy and more about narrative convenience, bending rules to serve timey-wimey storytelling. Yet even these fantastical depictions tap into a deeper truth. Wormholes symbolize humanity's yearning to explore, to leap beyond known horizons. Contact, based on Carl Sagan's novel, strikes a middle ground. Its wormhole transit sequence, a chaotic, visceral journey through tunnels of light, echoes theoretical ideas about turbulence and exotic matter, even if it skips the nitty-gritty math. What's fascinating is how these portrayals diverge from reality. Real wormholes, if they exist, wouldn't be polite doorways with neat edges. They'd likely be chaotic, unstable, and riddled with lethal radiation. The traversable wormholes of sci-fi often gloss over the need for exotic matter or the crushing tidal forces that would turn a human traveler into spaghetti. Event Horizon leans into this horror, imagining a wormhole as a hellish gateway to madness, a rare example where the science-adjacent dangers take center stage. Yet these creative liberties serve a purpose. They distill complex physics into visceral experiences, making abstract concepts tangible. When Thor's Bifrost Bridge visually echoes a wormhole or Avengers, in-game uses quantum tunnels for time heists, they're not aiming for realism. They're tapping into wormholes' cultural resonance as symbols of the unknown. The tension between scientific rigor and storytelling flair reveals something profound. Wormholes captivate because they live at the edge of possibility, a canvas for both our fears and our boldest dreams. Whether as rigorous thought experiments or narrative shortcuts, they remind us that the universe's mysteries are far stranger and more inspiring than fiction alone could conjure. While wormholes remain firmly in the realm of theory, NASA hasn't shied away from probing the edges of possibility. The agency's Innovative Advanced Concepts Program, or NIAC, has funded several speculative projects that flirt with wormhole-adjacent physics. One standout is a study led by physicist Luke Sellers, exploring something called negative energy, the very exotic substance that might stabilize a traversable wormhole. Using quantum field theory simulations, the team investigated whether tiny pockets of negative energy could be generated in the lab. The results inconclusive but tantalizing. It's a long way from propping open a cosmic tunnel, but it shows how even the wildest ideas can spark serious scientific inquiry. NASA's interest in wormhole physics isn't just about bending space, it's about rethinking propulsion. The Alcubierre drive, another NIAC-backed concept, borrows a page from wormhole theory by warping space-time around a spacecraft, effectively creating a bubble that moves faster than light without violating relativity. While not a wormhole itself, the drive relies on similar principles, manipulating space-time's fabric to cheat cosmic speed limits. Engineer Harold "Sonny" White, who led related experiments at NASA Eagleworks lab, once tested microscopic distortions using a device called a White-Jude interferometer. The goal: to detect even minuscule space-time warps that might hint at larger possibilities. Critics argue the effects observed could stem from experimental noise, but the effort underscores NASA's willingness to test far future ideas today. Beyond propulsion, NASA telescopes indirectly contribute to wormhole research by mapping the universe's gravitational extremes. The Event Horizon Telescope's landmark image of a black hole's shadow in 2019 wasn't about wormholes, but studying black holes' event horizons helps refine models of space-time's behavior under crushing gravity. If wormholes lurk in nature, they'd likely form in similar extreme environments. NASA's upcoming Nancy Grace Roman Space Telescope, set to launch in the late 2020s, could hunt for subtle gravitational lensing anomalies that might betray hidden cosmic structures, including, perhaps, the gravitational footprints of wormholes. Even NASA collaborations with quantum physicists edge toward wormhole-adjacent science. The agency has partnered with researchers exploring quantum entanglement's potential links to space-time geometry, echoing the ER EPR conjecture. In 2022, a team including NASA-affiliated scientists simulated a holographic wormhole using Google's Sycamore quantum processor. By encoding quantum bits to mimic entangled particles, they created a proxy for how information might traverse a wormhole. It wasn't a real space-time tunnel, but it hinted at how quantum systems might mirror wormhole physics. While no one at NASA is claiming imminent breakthroughs, their work reflects a quiet truth. The line between science fiction and science future is thinner than we think. By funding high-risk, high-reward studies from negative energy to quantum simulations, NASA keeps a door open to possibilities that might one day rewrite the rules of exploration. After all, today's thought experiment could be tomorrow's mission blueprint, and in that gap between what if and what is, wormholes linger, not yet real but no longer purely fantasy. If wormholes are cosmic shortcuts, then warp drives are more like cheating the speed limit. Both promise faster than light travel, but they play by wildly different rules. The Alcubierre drive, first proposed by physicist Miguel Alcubierre in 1994, doesn't rip through space-time like a wormhole. Instead, it warps the fabric of the universe around a spacecraft, compressing space in front of it and expanding space behind. Picture a surfer riding a wave. The ship stays stationary inside a warp bubble, while space itself moves at speeds that defy conventional limits. No tunnel, no portal, just space-time bending like rubber to carry you forward. The key difference: wormholes demand exotic matter to stay open, while warp drives require it to create the bubble in the first place. Both concepts hinge on negative energy, but Alcubierre's design might need less of it, at least in theory. Early calculations suggested the energy equivalent of converting Jupiter's mass into fuel, but refined models now hint at smaller, though still astronomical, amounts. There's another advantage: warp drives avoid the paradoxes and instability plaguing wormholes. No risk of collapsing mid-journey or spitting you out in the wrong epoch, just a relatively smooth ride. But don't pack your bags for Alpha Centauri yet. Warp drives come with their own deal-breakers. The radiation at the edges of the warp bubble would be lethal, frying anything nearby. And then there's the stop problem. Shutting down the bubble abruptly could release enough energy to vaporize your destination. Plus, creating the bubble in the first place might need materials that don't exist, like exotic matter with properties beyond anything we've observed. Feasibility comes down to which nightmare physics problem you'd rather tackle. Wormholes require stabilizing a chaotic, volatile tunnel. Warp drives need to harness and control titanic amounts of energy without blowing up the neighborhood. Intriguingly, warp theory has seen more practical research, like NASA Eagleworks experiments, but wormholes benefit from something warp drives lack: natural plausibility. Einstein's equations allow for wormholes even if they're unlikely. Warp drives, meanwhile, are purely human-made hypotheses with no natural analogues. So which wins? For now, neither. Both live in the realm of maybe one day, but the race between them reveals a deeper truth about our approach to the cosmos. Wormholes offer the allure of discovery, tapping into structures the universe might have built. Warp drives embody our ambition to reshape reality itself. One is a hidden backdoor, the other is a bulldozer, and the winner might not be the one that's possible, but the one that's survivable for anyone daring enough to try. The Fermi paradox presents a haunting question: if the universe is so vast and ancient, where is everyone? Given the billions of planets that could harbor life, why haven't we detected even a whisper of alien civilizations? One provocative answer might lie in wormholes. Imagine a galaxy where advanced species don't crawl between stars at sublight speeds but hop through cosmic shortcuts, rendering traditional space travel obsolete. If that's true, their presence wouldn't necessarily leave the radio signals or megastructures we've been scanning for. They'd move invisibly, their highways woven into the fabric of space-time itself. This idea flips the paradox on its head. Instead of asking why we haven't seen aliens, we might consider whether we're looking for the wrong signs. A civilization harnessing wormholes wouldn't need Dyson spheres or slow generational ships. They'd bypass the need for interstellar voyages entirely. Their infrastructure could be hidden in plain sight, undetectable portals linking worlds, leaving no trace of the energy-intensive journeys we assume they'd require. Even their communications might not rely on electromagnetic waves, but on quantum entanglement or some other physics we've yet to uncover. But there's a darker twist. Wormholes could also explain the absence of alien contact. If traversable wormholes demand exotic matter or unfathomable energy, perhaps only the most ruthless civilizations survive long enough to master them. Species might annihilate themselves before reaching that threshold, or worse, collapse their wormholes catastrophically, sealing off regions of space like cosmic dead ends. The Great Filter, a hypothetical barrier preventing life from advancing, could be tied to the instability of these very technologies. Then there's the eerie possibility that wormhole-using civilizations are here, just not in ways we recognize. Theoretical physicist John Archibald Wheeler once mused that advanced beings might manipulate space-time at the quantum level, existing as subtle fluctuations in the vacuum of space. If they've transcended physical forms, their presence could be as undetectable to us as bacteria are to a whale. Wormholes might not just be their transportation network, but their very habitat, a dimension of reality we're blind to. Ultimately, wormholes don't solve the Fermi paradox so much as reshape it. They suggest that the silence of the cosmos isn't proof of our solitude, but a hint that we're searching with the wrong tools. The universe's greatest civilizations might not shout across the void. They could be whispering through folds in space-time, waiting for us to learn the language of the fabric itself. Until then, the paradox remains not as a wall, but as a door we haven't found the key to. What if wormholes aren't just shortcuts through our universe, but gateways to entirely different ones? The multiverse theory suggests our cosmos might be one of countless bubbles in an infinite sea of realities, each with its own laws of physics and history. And if wormholes exist, they could be the secret tunnels stitching these disparate worlds together. Imagine a passageway where stepping through doesn't just take you to another star system, but to a universe where gravity is twice as strong or where time runs backward. This isn't just speculative fiction, it's a fringe but serious idea in theoretical physics, where the boundaries between science and philosophy blur. The concept hinges on the idea of bubble universes. According to some models of cosmic inflation, our universe might be one of many that sprouted during the Big Bang, each inflating like a soap bubble in a froth. These universes could float in a higher dimensional space, forever out of reach unless something like a wormhole pierced the boundary between them. The mathematics of string theory even allows for such bridges, where the throat of a wormhole doesn't terminate in our space-time but in another reality entirely. It's like poking a straw through the wall of a balloon into another balloon beside it, a tunnel through the multiverse. But how would these cross-reality wormholes differ from ordinary ones? For starters, they'd likely demand even more exotic physics. Stabilizing a wormhole within our universe is hard enough, but one that bridges separate cosmic bubbles might require energies far beyond anything we can conceive. Some theories suggest that the mouths of these wormholes could be anchored by cosmic strings, those ultra-dense filaments left over from the early universe, or by quantum foam fluctuations so intense they punch through into adjacent realities. The conditions needed would be so extreme that they might only occur naturally in the hearts of black holes or during the birth of universes. Then there's the question of what you'd find on the other side. A multiverse wormhole might not even lead to a universe remotely like ours. In some alternate realities, the fundamental constants could be tweaked. Electromagnetism might be weaker, making chemistry impossible, or the cosmological constant could be so large that space-time shreds apart instantly. Even if life exists in these other universes, it could be so alien that communication or even survival would be unthinkable. The sheer diversity of possible worlds is both exhilarating and humbling, a reminder that our universe's laws might be just one accidental arrangement in an infinite cosmic lottery. Interestingly, multiverse wormholes might solve some of the paradoxes that plague their single-universe counterparts. Time travel through a wormhole in our universe risks causality violations, like the grandfather paradox, but if the exit point lies in a separate reality, those paradoxes might dissolve. You couldn't change your own past, just the history of a parallel world. It's a loophole that turns time travel into universe hopping, sidestepping the messy consequences of altering established events. Of course, the biggest hurdle is evidence. Multiverse theories are notoriously hard to test, and wormholes bridging them doubly so. Some physicists propose looking for subtle gravitational anomalies, places where the pull of gravity doesn't match visible matter, hinting at unseen structures. Others suggest that high-energy particle collisions might, for a split second, create micro-wormholes that flicker in and out of existence, leaving behind telltale energy signatures. But for now, these ideas linger in the realm of mathematical elegance rather than observable proof. Yet the possibility lingers, tugging at the edges of our imagination. Wormholes as multiverse portals redefine not just travel but existence itself. They suggest that reality might be vaster and more interconnected than we ever dreamed. A cosmic web where every universe is just a step away if only we could find the door. Whether they're real or not, these theories remind us that the universe or multiverse is far stranger than we've dared to suppose, and that's a thrill no science fiction can match. Building a stable wormhole isn't just an engineering challenge, it's a cosmic scale puzzle that pushes the limits of known physics. The first hurdle, energy. To bend space-time into a traversable tunnel, you'd need to concentrate an almost inconceivable amount of mass or energy in one place. Some estimates suggest the energy equivalent of converting entire stars into pure gravitational potential, all focused on a single point. For context, humanity's total energy output in a year wouldn't even scratch the surface. Our most powerful particle accelerators, like the Large Hadron Collider, can't come close to the energies required to warp space-time meaningfully. It's like trying to dig the Panama Canal with a teaspoon. Then there's the exotic matter problem. Unlike normal matter that fills our everyday world, exotic matter would need to possess negative energy density, a property that defies gravity's usual rules. Picture a substance that repels rather than attracts, acting like anti-gravity glue to keep the wormhole's throat from collapsing. The catch: no such material has ever been observed in nature. Quantum mechanics hints that tiny amounts of negative energy might flicker in and out of existence at the subatomic level, but scaling that up to stabilize a macroscopic wormhole is like trying to build a skyscraper out of soap bubbles. Even if we could synthesize exotic matter, the quantities needed would dwarf the mass of Jupiter. Stability is another nightmare. Wormholes, by their nature, are intensely unstable. Without constant reinforcement, the immense gravitational forces at play would cause the tunnel to pinch shut faster than light could traverse it. Think of it like holding open a water-filled balloon with your fingers. The moment you relax, it snaps closed. To prevent this, you'd need a mechanism to exert continuous negative pressure throughout the wormhole's length, a feat requiring precision beyond anything our technology can achieve. And that's assuming the wormhole doesn't immediately degenerate into a black hole, swallowing all attempts to stabilize it. Radiation poses yet another lethal barrier. Any matter or energy passing through a wormhole would be bombarded by extreme tidal forces and high-energy particles, courtesy of the warped space-time environment. Even if you survived the gravitational spaghettification, the radiation would likely reduce any known material or living tissue to subatomic debris. Shielding against this would demand materials with impossible properties, like perfect superconductivity or the ability to reflect gamma rays like a mirror reflects light. Finally, there's the control problem. Suppose you somehow stabilize a wormhole, how do you steer it? Pinning one end to Earth while moving the other to a distant star would require accelerating the exit point to relativistic speeds, all while maintaining the wormhole's delicate balance. The energy needed for such precise manipulation rivals the output of a supernova. Even minor miscalculations could send the exit point careening into a black hole or destabilize the entire structure, collapsing it into a singularity. Yet the most sobering realization is this: our current understanding of physics might be fundamentally incomplete when it comes to wormholes. General relativity allows for their existence mathematically, but it doesn't account for quantum effects at such extreme scales. Until we unify quantum mechanics and gravity, a goal that's eluded physicists for a century, wormholes will remain tantalizingly out of reach. They're a reminder that the universe's most alluring possibilities often come with conditions we're not yet equipped to meet. But that's what makes the pursuit so thrilling. Every breakthrough in quantum theory or energy manipulation brings us one step closer to turning science fiction into science fact. So far, wormholes remain firmly in the realm of theory. But what if the universe has already left us subtle clues hidden in plain sight? Astrophysicists have scoured the cosmos for anomalies that might betray the presence of these cosmic shortcuts, and a few peculiar phenomena have sparked intrigue. Take gamma-ray bursts, those brilliant flashes of energy erupting from distant galaxies. Most stem from collapsing stars or neutron star collisions, but a handful defy conventional explanations. In 2015, astronomers detected GRB 070019, a burst lasting an unusually long 100 seconds, with a light curve that flickered in a way no known stellar explosion could produce. Some theorists speculate it might have been caused by a wormhole's throat snapping shut, releasing pent-up energy like an elastic band finally breaking. No conclusive proof exists, but the idea lingers like a tantalizing puzzle piece. Then there's gravitational lensing, where massive objects bend light like a magnifying glass. Normally, galaxies or black holes produce predictable lensing arcs, but what about when the distortion doesn't match any visible mass? In 2021, the Hubble Space Telescope spotted a pair of mirrored quasars, their light warped into identical images by an unseen cosmic lens. The kicker, no detectable mass lay between them to explain the effect. One fringe hypothesis suggests an invisible wormhole's gravitational field could have bent the light, acting as a phantom lens. Skeptics counter that dark matter clumps could explain it, but the mystery endures. Perhaps the most compelling anomaly lies in cosmic voids, vast, empty regions of space where galaxies are eerily scarce. Some of these voids emit faint, uniform radio waves with no obvious source. A bold theory proposed by Russian astrophysicists suggests these emissions might be the echo of a wormhole's mouth, its exotic matter interacting weakly with the cosmic microwave background. It's a stretch, but not impossible. After all, if wormholes exist, they wouldn't announce themselves with neon signs. They'd hide in the gaps, the unexplained, the data points that stubbornly resist conventional models. The search isn't just about spotting wormholes, it's about rewriting our cosmic rulebook. Every anomaly forces us to ask, are we seeing noise or the first whispers of a universe far stranger than we dreamed? Until we catch one in the act, these cosmic breadcrumbs keep the hunt alive, teasing us with the possibility that the universe's greatest shortcuts might already be mapped in the stars, waiting for us to decipher their coordinates. Imagine a future where wormholes are real and functional. What happens then? The power to cross galaxies in a heartbeat wouldn't just revolutionize travel. It would upheave societies, economies, and even our sense of identity. Who gets access to this technology? Would it be monopolized by governments, corporations, or the ultra-wealthy, creating an interstellar class divide where the privileged hop between stars while the rest of humanity remains earthbound? History shows us what happens when transformative technologies are controlled by a select few. Colonialism, exploitation, and unchecked power. Now amplify that to a cosmic scale. Then there's the question of weaponization. A wormhole could transport resources or troops. Picture a scenario where one nation controls the only stable wormhole to a resource-rich exoplanet, effectively holding an interstellar chokehold. Or worse, an aggressor could use a wormhole to deliver a weapon instantaneously, rendering traditional defenses obsolete. The moment a hostile actor figures out how to collapse a wormhole mid-transit, they've created the ultimate trap, stranding enemies in the void or shredding matter in a catastrophic implosion. The Cold War's nuclear brinkmanship would pale in comparison to wormhole-enabled warfare, but the dilemmas don't stop at borders. The environmental and cultural consequences could be staggering. What if an unstable wormhole leaks exotic matter into Earth's biosphere, mutating ecosystems beyond recognition? Or consider the cultural shockwaves human societies separated by light years might evolve in wildly different directions. Reconnecting through wormholes could trigger conflicts akin to colonialism's violent clashes, but with civilizations separated by millennia of divergent evolution. Would we even recognize or respect a society that developed on the other side of a wormhole? And then there's time. If wormholes enable time travel, the ethical quagmire deepens. Altering past events, even accidentally, could erase entire lineages or destabilize the present. Should there be a universal ban on retroactive interference, or would factions inevitably exploit it? The temptation to fix history's tragedies would be overwhelming, but every change risks cascading into unforeseen chaos. Wormholes don't just challenge physics, they force us to confront our own nature. Would we use them to unite, explore, and elevate humanity, or repeat the cycles of exploitation and control that have marked so much of our history? The answer might determine whether we survive our own ingenuity. Dark energy and wormholes might seem like entirely separate cosmic mysteries, one fueling the universe's runaway expansion, the other potentially bending space-time into shortcuts. Yet beneath the surface, they could be entangled in ways that rewrite our understanding of reality. Dark energy, making up roughly 68% of the universe's content, is the enigmatic force pushing galaxies apart at an ever-increasing rate. Wormholes, on the other hand, would require space-time to fold inward, defying this outward surge. But what if dark energy isn't just working against wormholes? What if it's the very thing making them possible? The key lies in negative pressure, a property both phenomena might share. Dark energy behaves like a kind of anti-gravity, stretching space itself. Some theories suggest this expansion could arise from a field with negative energy density, the same bizarre quality needed to prop open a traversable wormhole. Picture it like this: if dark energy is the universe's stretching force, certain configurations of it might also twist space-time into stable tunnels. The math gets dizzying here, but the implication is startling. Dark energy could be the universe's own exotic matter, lurking everywhere while hiding the blueprint for wormholes in plain sight. Not all models agree, of course. Some physicists argue that dark energy's uniform push would prevent localized space-time warps, smoothing out potential wormholes before they form. Others propose that dark energy's effects might vary wildly on microscopic scales, creating tiny, fleeting wormholes in the quantum foam, the froth of space-time at the smallest possible level. These microscopic tunnels wouldn't help you cross galaxies, but they could hint at a deeper link between cosmic expansion and space-time's hidden architecture. Then there's the elephant in the room: dark energy's acceleration. If the universe keeps expanding faster, could it eventually tear apart not just galaxies but the fabric of space-time itself? Some doomsday scenarios suggest a big rip where even atoms are shredded, but speculative theories counter that. Under extreme stretching, space-time might fracture into a network of wormholes, cosmic stitching holding reality together as it strains at the seams. It's a cosmic irony. The force speeding the universe toward chaos might also seed the structures that save it. The most tantalizing idea: dark energy and wormholes could be two sides of the same coin, different manifestations of space-time's underlying flexibility. Just as steam and ice are both water in different states, perhaps wormholes and cosmic expansion emerge from the same fundamental physics, waiting for us to decode their connection. Until then, the dance between these two mysteries reminds us that the universe's greatest secrets might not be isolated. They might be whispering to each other in the language of warped space and hidden dimensions. Long before Einstein penned his equations, ancient cultures were already dreaming of cosmic doorways tales that eerily echo modern wormhole theories. Take the Sumerians, whose cuneiform tablets describe shimmering portals called Dooku, where gods descended from the heavens. These stargates weren't just metaphors, they were depicted as physical thresholds often guarded by winged beings that connected the divine realm to Earth. The details are uncanny: swirling energy, sudden disappearances, and travelers emerging unchanged despite crossing impossible distances. Could these be garbled accounts of advanced technology or pure coincidence? The Hindu epic Mahabharata takes it further, recounting the hero Arjuna's journey through a celestial tunnel called the Akash Ganga. Guided by the god Indra, he passes through a luminous vortex that bends time itself, arriving in a realm where days stretch into years. The description mirrors the time dilation effects near a relativistic wormhole where gravity warps the flow of time. Even more striking is the ancient Tamil concept of Nadi Shastra, which speaks of hidden channels linking distant worlds, a phrase that could double as a wormhole's textbook definition. Then there's the Aboriginal Australian songlines, oral maps woven into creation stories that describe pathways crossing the land and sky. Elders speak of walking these routes and arriving in dreamscapes that exist outside ordinary time and space. Modern physicists might call that a traversable wormhole's exit point. Similar threads appear in Norse mythology's Bifrost, a rainbow bridge shattered during Ragnarok, described as a tunnel burning with fire that only the worthy could survive, a poetic parallel to the radiation and gravitational stresses plaguing real wormhole models. But the most provocative link comes from the Dogon people of Mali. Their oral traditions, dating back thousands of years, describe Sirius not as a single star but as a binary system, a fact only confirmed by telescopes in the 19th century. They claimed their ancestors visited Earth via a spinning portal from Sirius B, a white dwarf star. While skeptics argue cultural contamination, the precision of these accounts raises eyebrows. If ancient cultures witnessed wormholes in action, even fleetingly, their myths might be less fantasy and more fragmented first contact logs. The counterargument, of course, is pareidolia, our tendency to see patterns where none exist. Ancient people lacked the vocabulary of general relativity, so they framed inexplicable phenomena through the lens of gods and magic. A lightning storm becomes Zeus' wrath, a solar eclipse a dragon swallowing the sun. By that logic, wormhole-like myths might just be creative explanations for comets, auroras, or other celestial oddities. Yet the consistency across isolated cultures, from Mesopotamia to the Andes, suggests something deeper. Either humanity shares a collective subconscious fascination with portals, or these stories preserve half-remembered encounters with technologies we're only now beginning to fathom. Perhaps the truth lies somewhere between. Wormholes, as we understand them, are mathematical possibilities, not proven realities. But the persistence of these myths hints at an enduring human intuition that the universe holds hidden pathways waiting to be unlocked. Whether born of observation or imagination, these ancient tales remind us that the line between myth and science has always been thinner than we think. And sometimes the oldest stories light the way to the newest discoveries. At the smallest scales imaginable, the fabric of space-time isn't smooth and polished. It's a seething, bubbling froth alive with chaotic energy. This is quantum foam, a turbulent sea of fluctuations where the very concepts of here and now lose meaning. According to quantum mechanics, empty space is never truly empty. Instead, it crackles with particles and antiparticles popping in and out of existence, borrowing energy from the vacuum before vanishing again. But the foam's most mind-bending feature might be its fleeting tunnels, microscopic wormholes forming and collapsing trillions of times per second, far too small and brief for any human eye to detect. These mini wormholes wouldn't transport spaceships or even dust particles. Operating at the Planck scale, a distance so tiny it's a million billion times smaller than an atom, they're more like quantum hiccups in reality. Imagine the universe as a vast, stormy ocean. Quantum foam would be the spray at the surface, with wormholes appearing like bubbles that burst almost instantly. Some theories suggest these ephemeral tunnels could stitch together separate points in space-time, even if only for a fraction of a nanosecond. It's a dizzying thought. Every cubic centimeter of the air around you might contain countless invisible bridges to elsewhere, flickering in and out faster than light can cross them. Why doesn't this chaos affect our everyday world? The same reason you don't feel individual raindrops in a hurricane, the effects average out. At macroscopic scales, space-time appears smooth and predictable, masking the frenzy beneath. But zoom in far enough, and the orderly universe gives way to a quantum carnival where wormholes dance in the shadows. Some physicists propose that these fleeting structures could be the key to unifying general relativity with quantum mechanics, offering a way to reconcile gravity's cosmic pull with the probabilistic rules of the subatomic world. The catch: observing quantum foam directly is like trying to photograph a soap bubble with a sledgehammer. Our current tools are too crude, too large-scale to probe such infinitesimal realms. Yet indirect hints abound. The Casimir effect, where two metal plates in a vacuum inexplicably attract each other, might be the fingerprint of quantum foam's energy fluctuations. And if mini wormholes are real, they could leave faint imprints in high-energy particle collisions or gravitational wave detectors, tiny spikes in data where space-time itself momentarily buckled. What makes this idea truly radical is the possibility that these microscopic wormholes aren't just quirks of physics, they could be the scaffolding of reality itself. Some models of quantum gravity suggest space-time might be woven from a network of these vanishingly small connections, like threads in a cosmic tapestry. Every star, planet, or person would then be built atop a hidden lattice of ephemeral tunnels, their existence fleeting but their collective effect shaping the universe we know. For now, quantum foam remains a theoretical playground, a realm where mathematics outpaces measurement. But it challenges our most basic assumptions about space and time, suggesting that the smooth, continuous universe we perceive might be an illusion, a veneer over a far stranger, more dynamic truth. Whether these mini wormholes are cosmic static or the secret gears of reality, one thing is clear: the universe is far wilder at its roots than we ever dared to dream. The holographic principle turns our perception of reality inside out. What if the three-dimensional universe we experience is just a shadow, a projection of information encoded on a two-dimensional surface at the edge of space-time? It sounds like science fiction, but this radical idea emerges from black hole physics and string theory, and it might hold the key to understanding wormholes in an entirely new light. Picture the universe as a cosmic movie screen. Everything we see, stars, planets, even our own bodies, is like the flickering images on that screen, while the true source code of reality exists on the flat surface behind it. Now imagine wormholes as glitches or shortcuts in that projection, tunnels stitching together distant points not just in space but in the underlying data itself. This connection becomes clearer when we look at black holes, those cosmic shredders that seemingly destroy information. The holographic principle suggests that all the data swallowed by a black hole isn't lost, it's smeared across its event horizon like a celestial hard drive. Wormholes might act as hidden cables linking these horizons, ensuring information is preserved even as it appears to vanish. Physicists Juan Maldeisner and Leonard Susskind took this further with the ER EPR conjecture, proposing that entangled particles, those spooky twins of quantum mechanics, are secretly connected by microscopic wormholes. In this view, entanglement isn't just a quantum quirk, it's the holographic signature of a space-time tunnel too tiny to see. What's mind-bending is how this flips the script on wormhole geometry. Instead of thinking of them as physical tunnels burrowing through space, they might be more like pixelated shortcuts in the universe's underlying code. If the cosmos is a hologram, wormholes could be edits or rewrites in that code, allowing information to bypass the usual rendering process. Think of a video game where two distant locations are linked not by a visible bridge but by a shared line of programming, a warp in the rules rather than the graphics. The holographic principle also offers a fresh take on wormhole stability. In ordinary physics, keeping a wormhole open requires exotic matter with negative energy. But if space-time is fundamentally informational, stability might depend on maintaining coherence in the data. A traversable wormhole could be less about engineering and more about error correction, ensuring the bits on the two-dimensional boundary stay synchronized so the three-dimensional tunnel doesn't collapse. It's the difference between propping open a door with a brick and debugging a glitch in a simulation. This perspective even reshapes the paradoxes of wormhole time travel. In a holographic universe, altering the past might not create paradoxes but instead trigger updates in the cosmic code, rewriting history in a self-consistent way. Like hitting undo in a document, the changes ripple through the projection without breaking the underlying rules. Some theories suggest that black hole interiors, potential wormhole gateways, could be holographic reconstructions of distant regions, meaning falling into one might teleport your information elsewhere without ever moving through conventional space. Yet the most tantalizing implication is unity. The holographic principle bridges quantum mechanics and gravity, two frameworks that have resisted reconciliation for a century. If wormholes are holographic phenomena, they might not just connect places, they could reveal how the universe stitches together the very large and the very small. Every tunnel through space-time would be a living equation, a clue to how reality renders itself into existence. For now, these ideas remain at the frontier of theoretical physics, but they remind us that the universe's deepest truths often lurk where our intuition fails. Wormholes might not just be shortcuts through space, they could be glimpses into the operating system of everything. In 2022, physicists made headlines by simulating a holographic wormhole, not in deep space, but inside Google's quantum computer. This wasn't a physical tunnel, of course, but a clever encoding of wormhole physics into qubits, the building blocks of quantum computing. The team, including researchers from Caltech and NASA, programmed a simplified model of a wormhole's behavior using entangled quantum bits. When they manipulated one set of qubits, information instantly reappeared in another, mimicking how matter might traverse a real wormhole's throat. It was like playing a cosmic game of telephone, where the message bypassed the ordinary rules of space and time. While the simulation couldn't bend actual space-time, it offered something equally profound, a glimpse into how quantum entanglement and wormholes might be two sides of the same coin. Other labs have taken different approaches. At the University of Maryland, scientists used superconducting materials to create synthetic magnetic fields that twist space in ways reminiscent of wormhole geometry. By cooling a special chip to near absolute zero, they induced currents that flowed in paradoxical loops, behavior that mathematically mirrors the warped pathways near a wormhole's entrance. The effect was fleeting and microscopic, but it demonstrated how tabletop experiments can probe space-time's flexibility. Meanwhile, optical physicists in Vienna have crafted wormhole analogs using lasers and metamaterials. By bending light around specially designed structures, they've simulated how a wormhole might deflect radiation, a visual cheat sheet for predicting what real wormholes could look like. The most mind-bending attempts come from quantum gravity research. Teams at Fermilab and CERN are hunting for wormhole-like signatures in particle collision data. The idea, if two particles collide with enough energy, they might briefly stitch together a microscopic bridge in the quantum foam, a wormhole so small it lasts only a septillionth of a second. Detecting such an event would require spotting anomalous energy patterns like a faint echo in the debris. So far, no smoking gun, but the search continues. These experiments share a common thread. They're not building wormholes so much as reverse engineering the universe's cheat codes, whether through quantum entanglement, synthetic magnetism, or light manipulation. Scientists are testing whether space-time's rulebook allows for shortcuts, and if so, how we might one day crack them open. Every simulation, no matter how abstract, brings us closer to answering whether wormholes are cosmic mirages or hidden doors waiting to be unlocked. The lab might be where science fiction becomes science fact, one qubit at a time. Could the birth of the universe itself have been shaped by wormholes? The Big Bang remains the most explosive mystery in physics, an event where space, time, and the laws of nature as we know them all came screaming into existence. But what if the universe's first moments weren't just a chaotic fireball, but a labyrinth of wormholes stitching together the fabric of reality before it even cooled? Some cosmologists speculate that in the extreme conditions just after the Big Bang, space-time might have been so warped and turbulent that wormholes could have formed naturally, like bubbles in a boiling pot of cosmic soup. These primordial wormholes wouldn't resemble the tidy portals of science fiction. Think instead of fleeting, quantum-scale tunnels twisting and collapsing in the seething plasma of the early universe. Inflation theory suggests that space expanded faster than light in the first fractions of a second, smoothing out the cosmos into the vast, uniform expanse we see today. But what if wormholes were part of that process? One radical idea proposes that inflation wasn't just a uniform stretching of space, but a fractal branching, with wormholes acting as cosmic stitching between rapidly inflating regions. Picture a growing foam where the bubbles are connected by microscopic tunnels, each one a shortcut that helped balance the universe's explosive growth. Even stranger, some models suggest these early wormholes could have seeded the large-scale structure of the cosmos. Today, we see galaxies arranged in vast filaments and voids, a cosmic web stretching across billions of light years. If wormholes threaded through the infant universe, their gravitational fingerprints might have nudged matter into these patterns, like invisible hands sculpting the first clusters of stars and galaxies. Dark matter, that enigmatic substance holding galaxies together, could even be tangled up in this story. If certain types of wormholes persisted, they might have decayed into exotic particles that now make up the universe's hidden mass, lurking unseen but shaping everything we observe. Then there's the wildest possibility of all, that the Big Bang wasn't a solitary event but a gateway. Some hypotheses in loop quantum gravity and string theory suggest our universe might have been born from a wormhole-like bridge connecting to another, older cosmos, a cosmic rebirth where one universe's collapse becomes another's explosion. In this scenario, the Big Bang wasn't the absolute beginning, but a violent transition, like a black hole in a parent universe birthing our own through a space-time tunnel. It's a dizzying thought that every star, planet, and person might trace back to a wormhole's echo from a reality that existed before time itself. Of course, evidence for any of this remains elusive. The Planck era, the first sliver of time after the Big Bang, is shrouded in energy so extreme that our current physics breaks down. Probing that epoch would require particle accelerators the size of solar systems or telescopes sensitive enough to detect primordial gravitational waves imprinted on the cosmos like faint scars. Yet the very possibility reshapes how we view the universe's origins. Wormholes aren't just potential tools for future explorers. They might be cosmic relics, fossils from the instant everything began. And if they played a role in creation itself, their secrets could hold the key to understanding not just where we're going, but where we came from. The sheer scale of the cosmos is both awe-inspiring and paralyzing. Even our nearest stellar neighbor, Proxima Centauri, sits over 4 light-years away. At the speeds of today's fastest spacecraft, reaching it would take tens of thousands of years. But wormholes could turn that grueling odyssey into a stroll across the threshold. Picture a future where interstellar travel isn't about enduring generations in cryosleep or weathering the hazards of deep space, but stepping through a shimmering gateway and emerging in another star system before your coffee cools. The implications are staggering. Colonies on distant exoplanets, resource mining in asteroid belts light years away, even diplomatic ties with alien civilizations, all become plausible when distance is no longer a barrier. Consider the Milky Way, a sprawling disk of stars 100,000 light-years across. Conventional rockets could never hope to explore even a fraction of it within a human lifetime. But with a network of stable wormholes, the galaxy effectively shrinks. A trip to the galactic core, which would normally take 30,000 years at light speed, could become a day trip. The concept isn't just about speed, it's about accessibility. Entire regions of space that were once unreachable backwaters could transform into bustling hubs. Imagine a trading post near the supermassive black hole at our galaxy's center, where exotic matter or gravitational anomalies are harvested, all because a wormhole placed it within practical reach. There's a psychological revolution here too. For centuries, humanity has dreamed of the stars while feeling imprisoned by the vastness between them. Wormholes shatter that confinement. They redefine what it means to explore, shifting the challenge from surviving the journey to mastering the destination. A Mars mission today requires battling radiation, muscle atrophy, and isolation. A wormhole-enabled mission to a habitable exoplanet. The obstacles shift to diplomacy, ecology, and cultural exchange. The frontier isn't the void anymore, it's the worlds waiting on the other side. Yet the true game changer might be time. Even at light speed, interstellar travel is a one-way ticket to the future due to relativity's time dilation. A crew visiting a star 50 light-years away would return to an Earth a century older. Wormholes could circumvent this by threading space-time in a way that sidesteps the time-stretching effects of high velocity. Arrive, explore, and return without leaving your own era. It's the difference between sending out generational arcs and establishing a true interstellar community where families aren't fractured by centuries. Of course, the practical hurdles are monumental. Stabilizing a wormhole large enough for a spacecraft demands technologies we can barely envision, and the energy costs border on the mythical. But history shows that today's impossibilities are tomorrow's engineering challenges. The transcontinental railroad, the Panama Canal, the internet, each seemed insurmountable until it wasn't. Wormholes represent the next great infrastructure project, just on a cosmic scale. The greatest adventure isn't building the ships to cross the void. It's unlocking the doors that make the void irrelevant. Kip Thorne, the Nobel Prize-winning physicist who consulted on Interstellar's stunning wormhole visuals, once described these cosmic tunnels as the ultimate cheat sheet for the universe. He didn't dismiss them as fantasy. His calculations showed that wormholes could theoretically exist within the framework of general relativity. But he also cautioned that nature seems to conspire against them, erecting a series of cosmic keep-out signs, like the need for exotic matter and the threat of instant collapse. Thorne's work revealed a tantalizing truth. The universe's laws might allow wormholes, but they've stacked the deck to make them nearly impossible to sustain. Stephen Hawking took a more skeptical view. In his characteristically wry style, he proposed the chronology protection conjecture, a cosmic rule preventing time travel to avoid paradoxes. If wormholes could bridge time as well as space, Hawking argued, the resulting chaos would violate causality, leading to absurdities like someone going back to prevent their own birth. The universe doesn't issue round-trip tickets to the past, he quipped. Yet even Hawking conceded that quantum mechanics might leave loopholes, suggesting microscopic wormholes could flicker in and out of existence at the Planck scale, far too small for human use but hinting at space-time's hidden flexibility. Carl Sagan, ever the poetic bridge between science and wonder, saw wormholes through a different lens. While writing Contact, he sought Thorne's advice to ensure his fictional wormhole felt scientifically plausible. Sagan envisioned them not just as engineering challenges, but as metaphors for humanity's hunger to explore. "The universe is under no obligation to make sense to us," he often remarked, "but that doesn't mean we stop asking." His perspective reminds us that wormholes captivate not just because they might be real, but because they reflect our deepest yearning to leap beyond limits, whether physical or imaginative. Contemporary voices add fresh insights. Michio Kaku compares stabilizing a wormhole to trying to build a bridge out of smoke, emphasizing the fragility of these structures. But he also speculates that a type Roman III civilization on the Kardashev scale, one harnessing the energy of entire galaxies, might crack the code. On the other hand, Lisa Randall, a leading string theorist, suggests wormholes could be relics of higher dimensional physics, hidden in plain sight if only we knew how to perceive extra dimensions. The chorus of scientific opinion reveals a spectrum of belief, from cautious optimism to outright skepticism. Yet what unites these thinkers is the recognition that wormholes, real or not, force us to confront the universe's most profound mysteries. They're not just about shortcuts through space, they're stress tests for our understanding of reality itself. Every equation, every debate, every tantalizing "what if" pushes the boundaries of what we consider possible. And in that sense, wormholes have already taken us further than we ever imagined. The idea that wormholes might bridge not just distant points in our universe, but entirely separate dimensions, feels like something ripped from the pages of a multiverse saga. Yet this notion isn't just science fiction, it's a serious avenue of exploration in theoretical physics. Imagine a wormhole not as a tunnel through space, but as a seam stitching together alternate realities, each with its own unique laws of physics and history. String theory, one of the leading frameworks for unifying quantum mechanics and gravity, suggests our universe might be a three-dimensional brain floating in a higher dimensional space called the bulk. In this scenario, wormholes could be conduits piercing through the bulk, linking our brain to others like pores in a vast cosmic sponge. The math behind this is dizzying, but the implications are profound. If such cross-dimensional wormholes exist, they wouldn't just transport matter, they might allow the very rules of reality to bleed through. Picture stepping into a wormhole in our universe and emerging in a dimension where gravity is repulsive or where time flows backward. Some models even propose that dark energy, the mysterious force accelerating the universe's expansion, could be the gravitational pull of a neighboring brain leaking through a wormhole's throat. It's a concept that reshapes not just how we think about travel, but about the nature of existence itself. Parallel realities add another layer of complexity. The many worlds interpretation of quantum mechanics suggests every decision spawns alternate timelines, branching endlessly like a fractal. Could wormholes thread these branches together? Theoretically, yes, but the consequences are mind-bending. A wormhole linking two timelines might allow observation or even interaction with alternate versions of history. Imagine a portal to a world where the dinosaurs never went extinct or where humanity never evolved. The catch: stability. Cross-dimensional wormholes would likely require even more exotic stabilization than their interstellar cousins, perhaps drawing energy from the vacuum between brains or relying on higher dimensional physics we've yet to discover. Then there's the ultimate question: if such wormholes exist, could we ever detect them? Some theorists suggest hunting for gravitational anomalies that defy conventional explanation, places where the pull of gravity seems to vanish or reverse without a visible source. Others propose that high-energy particle collisions might momentarily puncture the fabric of our brain, creating micro-wormholes that flicker into higher dimensions before sealing shut. These wouldn't be traversable tunnels, of course, but their signatures could reveal the hidden architecture of the multiverse. The most tantalizing and unsettling possibility is that cross-dimensional wormholes might already be in use by something else. If advanced civilizations in other branes have mastered dimensional travel, their infrastructure could be all around us, invisible only because we lack the tools to perceive higher dimensional geometry. It's a humbling thought. The cosmos might be teeming with gateways we're blind to, hidden in plain sight like shadows on a cave wall. Whether wormholes bridge dimensions or not, the mere possibility forces us to confront how little we understand about the universe's true shape. They remind us that reality might be far richer, stranger, and more interconnected than our three-dimensional intuition allows. And that's the real magic of theoretical physics, not just answering questions, but discovering how much more there is to ask. What if wormholes aren't just corridors through space-time, but pathways for consciousness itself? This fringe theory blurs the line between physics and metaphysics, suggesting that these cosmic tunnels might interact with the human mind in ways science can't yet explain. Proponents point to bizarre anomalies, near-death experiences describing tunnel-like visions, sudden psychic intuitions of distant events, or even alleged cases of teleportation in ancient texts. The common thread, a perceived connection between altered states of awareness and shortcuts through reality's fabric. While mainstream science dismisses these ideas as pseudoscience, the parallels are eerie enough to spark curiosity. Consider the accounts of those who have clinically died and revived, often reporting tunnels of light or instantaneous travel across vast distances. Skeptics attribute these to oxygen deprivation or firing neurons, but what if the dying brain temporarily perceives or even accesses a fundamental layer of space-time normally hidden from view? Some theoretical physicists speculate that consciousness might not be confined to the brain but intertwined with space-time structure. In this view, a wormhole could act less like a physical passage and more like a bridge between minds, allowing information to bypass conventional limits. Then there's the enigma of psychic phenomena. Remote viewing experiments where individuals attempt to perceive distant locations have yielded occasional hits that statistically defy chance. Could these successes hint at latent human ability to tune in to wormhole-like connections in the quantum foam? It's a stretch, but not entirely implausible when you consider quantum entanglement's spooky linkages. If particles can instantaneously influence each other across light years, could consciousness exploit similar shortcuts? The CIA's now declassified Stargate project, which explored psychic espionage, even borrowed terminology from wormhole physics, though its results remain hotly debated. Ancient mystics add another layer. Tibetan Buddhist monks speak of rainbow body ascension, where adepts allegedly dissolve into light and reappear elsewhere. Indigenous shamans describe traversing spirit tunnels to access hidden realms. While these traditions use spiritual frameworks, their descriptions uncannily mirror modern wormhole concepts. Either humanity independently imagined similar metaphors for transcendence, or these stories preserve encounters with phenomena we're only now beginning to model mathematically. The catch, not a shred of empirical evidence supports consciousness wormhole links. Neuroscience firmly roots awareness in the brain's biology, not cosmic tunnels. Quantum effects, while strange, operate at scales too tiny to influence macroscopic thoughts, and every supposed psychic breakthrough crumbles under rigorous testing. Yet the persistence of these ideas across cultures and eras suggests something profound, even if it's just the universal human longing to bend the rules of existence. Wormholes captivate because they promise liberation from physical limits. Consciousness fascinates because it defies material explanations. Merging the two might be more poetry than physics, but it's poetry that keeps us reaching for the stars and questioning what lies beyond. The next 50 to 100 years of wormhole research could unfold like a cosmic detective story, with scientists chasing clues across quantum labs and distant galaxies. One promising frontier lies in quantum gravity, the holy grail of modern physics that seeks to merge Einstein's relativity with the bizarre rules of the quantum world. Breakthroughs here might reveal whether space-time's fabric is fundamentally smooth or woven from microscopic wormholes, a concept dubbed space-time foam. Imagine particle accelerators 1,000 times more powerful than today's, slamming matter together at energies that briefly mimic the Big Bang's conditions. These collisions could create fleeting wormholes smaller than atoms, detectable only by their telltale energy signatures, like catching a ghost shadow on a detector screen. Labs like the Future Circular Collider, proposed to dwarf the Large Hadron Collider, might become wormhole hunting grounds by mid-century. Meanwhile, astrophysics could shift from speculation to active observation. Next-generation telescopes like the Laser Interferometer Space Antenna LISA, set to launch in the 2030s, will map gravitational waves with unprecedented precision. Subtle anomalies in these ripples, perhaps echoes from colliding black holes, might betray hidden wormholes warping space-time nearby. By the century's end, astronomers might deploy dedicated wormhole observatories, scanning the cosmos for gravitational lensing patterns that no black hole or dark matter could explain. Picture a sky not just mapped by stars, but by secret tunnels threading the void. The wild card artificial intelligence, machine learning algorithms could sift through petabytes of quantum and astronomical data, spotting wormhole signatures humans might miss. AI-designed experiments might even uncover exotic matter analogues in unconventional materials, like metamaterials that mimic negative energies effects. Quantum computers, leveraging entanglement's weirdness, could simulate wormhole dynamics at scales impossible for classical machines, essentially recreating them in silicon before we build them in reality. Yet the biggest leaps may come from rethinking fundamental assumptions. If dark energy's nature is unlocked, it might offer a cosmic shortcut, literally. Some theories suggest dark energy's repulsive force could be harnessed to stabilize wormholes, turning the universe's expansion mechanism into a construction tool. Or perhaps higher dimensional physics, once confined to string theory papers, will yield practical insights. Experiments probing extra dimensions like searches for leaking gravity in particle colliders could reveal wormholes aren't tunnels at all, but folds in a multidimensional fabric we're only beginning to perceive. By the 22nd century, wormhole research might transition from theory to engineering. Imagine teams not just observing natural wormholes, but coaxing them into existence using controlled quantum chaos or space-time stitching techniques. The first stable microscopic wormhole could emerge in a lab, a proof of concept bridging centimeters before light years. Ethical and safety debates would rage. Could a man-made wormhole accidentally siphon Earth's atmosphere or trigger a space-time rupture? Regulations might rival nuclear treaties in their severity. Ultimately, the future of wormhole science hinges on a deeper truth. The universe's rules are still being written. Every dead end in quantum gravity, every anomalous gravitational wave, and every AI-generated aha moment brings us closer to answering whether wormholes are cosmic flukes or inevitable features of reality. One day, a child gazing at the stars might not wonder if wormholes exist, but how to book passage through one. And that's the real thrill of science. The journey from impossible to inevitable is often just a matter of time. Wormholes have inspired countless myths, from apocalyptic prophecies to Hollywood-fueled fantasies, but how many hold up to real physics? Let's start with the most dramatic claim, that wormholes are supernatural gateways to hell or other dimensions. This idea often stems from conflating wormholes with black holes, those cosmic vacuum cleaners that crush matter into oblivion. While black holes have been unfairly demonized as evil, wormholes are fundamentally different. They are hypothetical bridges, not shredders. No credible science suggests they'd unleash demons or cosmic horrors. The closest thing to hell inside a wormhole. Probably just lethal radiation and crushing tidal forces, hazards grounded in astrophysics, not theology. Then there's the time travel trope. Movies love showing characters hopping through wormholes to rewrite history, but reality is far messier. Einstein's equations do allow for wormholes connecting different times, but here's the catch. They'd require conditions so precise they border on absurd. To become a time machine, a wormhole's ends would need to be moving at relativistic speeds or placed near black holes to exploit time dilation. Even then, quantum effects might trigger a feedback loop of destructive energy the moment you try to change the past, collapsing the tunnel. Physicist Stephen Hawking called this the chronology protection conjecture, a cosmic failsafe that stops paradoxes before they start. So while time travel isn't ruled out mathematically, nature seems rigged to prevent it. Another myth, that wormholes would look like shimmering, human-sized portals ready to step through. In reality, a naturally occurring wormhole would more likely resemble a black hole's event horizon, a near-invisible boundary where space-time folds. Any visible distortion, like the lens-like ring in Interstellar, would stem from extreme light-bending effects, not Hollywood neon, and don't expect a smooth ride. Without exotic matter to stabilize it, crossing would be like surfing a collapsing wave of space-time, with gravitational forces stretching you into spaghetti long before you reach the other side. Perhaps the most persistent misconception is that wormholes are just waiting to be discovered, cosmic subway stops for advanced civilizations. The truth is grimmer. Even if they exist, most theoretical models suggest wormholes would be microscopic, unstable, or hidden inside black holes places no probe could reach. The idea that aliens or humans are already using them hinges on technologies we can't begin to engineer, like harvesting negative energy or taming singularities. It's not impossible, but it's like assuming cavemen could build smartphones because silicon exists in nature. Finally, pop culture often treats wormholes as two-way doors, but physics allows for one-way models too. Picture a drain where you're flushed in but can't return, a brutal exit with no comeback. Even traversable wormholes might only permit single journeys if their structure shifts after transit. So much for weekend trips to Andromeda. Dispelling these myths isn't about killing wonder, it's about redirecting it. Wormholes aren't magic, they're math. And that makes them even more astonishing. The universe doesn't need demons or time loops to be thrilling. The simple fact that space-time might fold, even under conditions we can't yet harness, proves reality is stranger than any myth we've invented. The truth isn't hiding in superstition. It's written in the equations, waiting for us to decode them. Wormholes stand at the crossroads of human imagination and scientific possibility, bridges between the known and the unfathomable. On one hand, they offer a vision of interstellar travel so revolutionary it would render light speed obsolete, collapsing the vastness of space into something as navigable as a subway map. Imagine stepping through a portal and emerging near a planet orbiting Vega, or shaking hands with a civilization from another galaxy. The cultural, philosophical, and technological leaps this would trigger are almost beyond comprehension. Entire economies could form around wormhole transit, with trade routes linking star systems like cities on a highway. The very concept of home might expand to include multiple worlds, each a doorstep away. Yet for all their promise, wormholes remain shrouded in daunting challenges. The exotic matter needed to stabilize them still theoretical, the energy required to keep them open comparable to harnessing entire stars. Even if we overcame these hurdles, the ethical dilemmas would be staggering. Who controls access to these cosmic shortcuts? Could they become weapons, bending not just space but the balance of power? And what happens if a wormhole collapses mid-transit, stranding travelers or worse, altering the fabric of causality itself? The universe doesn't hand out user manuals for rewriting the rules of reality. Perhaps the most profound question isn't whether wormholes exist, but whether we're prepared for what they demand of us. Mastery over space-time isn't just a technological feat, it's a test of wisdom. History shows that humanity often races ahead with discovery before grappling with its consequences. Would wormholes unite us as an interstellar species or deepen our divides? Would we use them to explore with curiosity or exploit with greed? The answer might reveal less about the universe's secrets and more about our own readiness to grow beyond the limits of our planet. So here's a thought to leave you with. If a stable wormhole appeared tomorrow, ripe for travel, would humanity be ready for what comes next? Would we step through with wonder or wariness? The future isn't just written in the stars, it's shaped by the choices we make here and now. Drop your theories in the comments below, and don't forget to subscribe for more deep dives into the science and soul of tomorrow's possibilities. The cosmos is full of mysteries waiting to be unraveled. Who knows which one we'll explore?